Okay, yeah, so let's continue now talking about processing near memory architectures, and we are going to focus on near memory, processing near memory architectures that, let me see if I can close this. Okay, processing near memory architectures that are real, are already in the real world. Onur has introduced processing near memory, and he has talked about some academic proposals such as PEI or Tesseract, or the work that we did with different Google workloads. And that's, I think, really interesting work that has somehow opened the later developments in the real world from different companies in industry, both startups and major vendors. Remember that we are talking here about two main approaches to processing in memory. This text here and the table comes from the book chapter that Onur mentioned earlier. These two main approaches are processing using memory, that we will talk later about, and processing near memory. There are different ways of doing processing near memory depending on where you place the compute units, and also depending on what are those compute units. But today we are going to focus on those that already exist either in the market or have become prototypes and have been announced and tested by the corresponding vendors. So the first ones to announce a real-world processing in memory system was AppMem, which is a French startup settled in Grenoble. And they did that in sometime between 2016 and 2019. They developed their system and they released it. And a couple of years later, in early 2021, Samsung announced the HBM PIM architecture, also called PIM DRAM. Later, the same year at Hot Chips, they also announced PIM systems for LPDDR5 and for DIM, DDR4 DIMMs. We are going to talk about them briefly in a few minutes. And last year, about 1 year ago, SK Hynix also announced their own architecture called Accelerator in Memory. And also in the same conference, ISSCC, Alibaba announced HBM-PNM, the HB-PNM, that is one of the, we are going to have Dimi New talking about one of these, talking about this architecture. I'm going to start with AppMem PIM. I will give you an introduction to the architecture. Then we will briefly go over the different proposals or the different prototypes that different vendors have announced. And at the end, or in the second part of the talk, we will focus on how to program AppMem PIM, because that's what we need, or you need to know, in order to do the hands-on lab this afternoon. So this is a slide from Onur. You have probably seen it before. Basically, the AppMem PIM system is a processing in DRAM system. It's built on DDR4 modules, and inside each of the chips, there are called PIM chips. There are memory arrays as usual, DRAM memory arrays as usual, but there are also small processors that are called DRAM processing units, or DPUs. And this is how these DIMMs look. This is one of the earlier prototypes that they developed, consisting only of 8 chips, in total 1 rank, in total 64 DPUs, 64 in-order PIM cores. More recently, they already started to fabricate dual rank DIMMs with up to 16 chips. And this is a picture of the system that you will have access to this afternoon. It's as you can see, it contains it's a dual socket CPU, as you can see on the picture, CPU 0 and CPU 1, and then both CPUs have access to DDR4 DIMMs, conventional DRAM that is still used as main memory, and then the PIM-enabled DIMMs, that is the AppMem DIMMs that are the PIM-enabled memory. We have worked extensively on understanding and characterizing this system, and this is one paper that we published last year. You can access it in archive, and also at the very bottom you can see the link to the repository where all the codes that we develop are publicly available. So let's start talking about the UPMEM PIM architecture. And I usually like to start some of these talks taking a look at the patent, because I think that the abstract of the patent very clearly defines what the UPMEM PIM architecture is. It's a memory circuit with a memory array, and near the memory array, there is a first processor. This first processor is the PIM core or the DPU. And there is a control interface for a central processor, the host CPU, to send commands to the PIM processor, to the first processor or the PIM core. The banks become available to the host processor when the PIM core is not working anymore with the data that resides in the memory bank, and the other way around. So at this point, at least in the current generation, it's not possible to have concurrent accesses from both the PIM core and the CPU. And this is a picture also from the patent of the overall system organization. Here you can see a system on a chip, and these are the different chips. Inside the different chips, we have the memory arrays, and also we have the processors. And this is another picture, maybe even more simplified, where you can see the host CPU, main memory DIMMs, and PIM-enabled DIMMs. And if we take a closer look at these PIM-enabled DIMMs, and we take a closer look at the memory chips, PIM chips, we can see that inside each of the PIM chips, we have 8 DRAM banks that UPMEM calls main RAM or MRAM. We're going to call them MRAM banks over the course of these talks. Each of them is 64 megabytes, and near each of the MRAM banks, there is a PIM processor, a PIM core that is called DRAM processing unit or DPU. And as you can see, we have 8 DPUs per chip, so in total 64 DPUs per rank. Feel free to ask any question at any time, please. So we can take a closer look at the DRAM processing unit. This is also from the patent. Remember that that's one of the chips, and inside the chips, we have all these different slices that represent the memory banks. This is one of the memory banks, and here you can see the core itself with the instruction memory, with the pipeline, and with the local memory. But I think that this figure here can be more clear. Inside the PIM chip, there is a control or status interface for the host processor to communicate with the DRAM processing units. There is a DDR4 interface for the host processor to access the DRAM banks. Then we have the 64 megabyte DRAM banks called MRAM, remember, and the way of accessing from the PIM core side, the way of accessing the MRAM bank is through a DMA engine. Using this DMA engine, we can move instructions to the 24 kilobyte instruction RAM. It's an instruction memory, it's not an instruction cache. So keep that into account. The largest size of the program that you run on the DPU is 24 kilobytes. And then we also have so-called WRAM or working RAM, which is a scratch pad. It's SRAM based and is used to store operands that will be accessed by the pipeline. The size of this WRAM is 64 kilobytes. And this is the pipeline. We can take a closer look at the pipeline here. In total, there are 14 pipeline stages. The normal thing that you can expect in an in-order processor: dispatch for thread selection, instruction fetch, access to the register file, operand formatting, the ALU stage to either use the ALUs or to access the WRAM, and finally the stages for result formatting. This pipeline is fine-grained multi-thread and can have and has up to 24 hardware threads. And it's an in-order pipeline that runs at a frequency, well, it ran at a frequency of 350 megahertz when we were working for the first time with the system. Now there are DIMMs with chips running at 400 or DPUs running at 425 megahertz. I'm pretty sure that all of you are familiar with fine-grained multi-threading, but if you want to have a very quick brush up, fine-grained multi-threading is an execution technique that basically interleaves the execution of instructions from different threads. And that's a way of avoiding data dependencies in the pipeline. And that's what UPMEM does in order to make sure that the pipeline is completely full and you don't need any complex unit inside the pipeline to do forwarding or to install threads, etc. So if you want to recap more on fine-grained multi-threading, this is here you can find a link to one of Onur's lectures. So yeah, exactly. Going back to the DPU pipeline, remember that in total we have 14 pipeline stages, and this number gives us already an orientation of what's the number of threads that we should, minimum number of threads that we should use in order to maximize the performance of the DPU. So the instruction set architecture is a specific 32-bit ISA. It's RISC, but it's not RISC-V, and it's aimed at scalar, in order, and multi-thread implementation. It allows compilation of 64-bit C code, but registers are 32 bits, and admin provides an LLVM clan compiler. If you want to take a look at some code, here you can see it at the very bottom. This is the code that corresponds to one of the micro benchmarks that we created when we were analyzing the architecture in order to measure the throughput of 32-bit integer addition. So at the top, you see the C-base code that we wrote. This is the for loop. So basically, in this code, what we are doing is we are moving a chunk of data of this size. We are moving it from the MRAM, which is the DRAM bank, to the WRAM, which is the scratchpad, and then the threads will go over all the elements that you have loaded into the scratchpad and performing some operation. In this case, adding one scalar. This buffer A is the space that we allocate in WRAM. In principle, each thread can have its own buffer A, but these pointers can also be shared across the different threads that run on the DPU, and so that the WRAM can be used as a shared memory in some way, in a similar way to the shared memory in NVIDIA GPUs, for example. And here at the bottom, you can see the compiled code with the DPU ISA. It's, as you can see, pretty simple to understand, reminds me MIPS or other other in-order ISAs. This is the address calculation and load from WRAM. This is the add operation, and this is the store to WRAM. So I'm not going to go into many details about the architecture because we don't have so much time, but there are some links here for you to, if you are interested, you can access them and learn more details about the DPU, the pipeline, and the architecture itself, or otherwise you can go to the paper. So before I continue, I want to give you some key takeaways of our work, because I think that they are going to clarify a lot about how the architecture performs. This is some analysis that we did, operational intensity or arithmetic throughput versus operational intensity. As you can see on the plot, the y-axis is the arithmetic throughput in mega operations per second. The x-axis is the operational intensity. As we increase the operational intensity, the arithmetic throughput also increases until at some point it saturates. This part with the where the compute throughput is flat is what we call the compute bound region. And one other thing that you can observe is that all these different dots here correspond to the number of threads, or the number of PIM threads that we needed to achieve certain performance. One thing that you can observe is that in the memory bound region, the number of threads to reach the maximum arithmetic throughput is relatively small, maybe 1, 2 in the very beginning, but at some point, until after we reach this throughput saturation point and we enter into the compute bound region, we need to use as many threads as those that are needed to keep the entire pipeline full. And this number in particular is 11. One thing that you also can observe is that the operational intensity where this throughput saturation point happens is extremely low. It's 1 integer addition per every 32-bit element. If you are doing that, then you're already reaching the compute bound region. So the key takeaway number 1 is that the admin PIM architecture is fundamentally a compute bound architecture. So we expect that it's going to be suitable for workloads that are memory bound in conventional processor-centric systems. We also perform a comparison to CPU and GPU. You can see on this plot the speed up over CPU for some workloads that we consider more PIM suitable because they perform better, they outperform a GPU. In this case, we compare to an NVIDIA Titan V. they outperform the NVIDIA at least the larger PIN system, because you can see that there are two different PIN systems. The larger one with 2,565 DPUs outperforms the GPU. For some other workloads, it did not perform the GPU, and those are the ones that we call the less PIN suitable workloads. But the key observation here is that the workloads that are more suitable for the PIM architecture and those that cannot perform the state-of-the-art GPU have three key characteristics. The first one is that they have streaming memory accesses, because that's the way of maximizing the memory bandwidth of each of the individual DPUs or PIM cores. There is no or little inter-DPU synchronization, and we will see soon why this is important, basically because there is no direct communication channel across DPUs. And the third one is that there is no or little use of integer multiplication, integer division, or floating point operations. Because even though this is a general purpose architecture and supports many different operations, there are some operations, more complex ones, as the ones you can see read on the slide, that are not supported natively. So they are emulated. So if you are using them, then performance won't be that great. So if these three characteristics are fulfilled by a workload, is good for the PIM architecture. Another key takeaway is that, is what I just read, actually. Key takeaway number 2 is that the best or most suitable workloads for the PIM system use no arithmetic operations or only simple operations, and they also have little or no communication. And here, as a summary, you can see some numbers for the comparison to CPUs and GPUs. If you go back to the previous slides, you will see that for most of the PIM benchmarks, the larger for most of the benchmarks that we evaluated that are called PIM benchmarks, the larger PIM system outperform the CPU, and for a majority of them, in total 10 out of 16, it outperformed the state-of-the-art GPU. We believe that the future is even more positive for these kind of systems. In terms of energy efficiency, we can see that for those workloads where the admin systems provide performance improvements, they can also provide significant energy savings. And this is the link to the repository that I also mentioned earlier. PNM is not the only one that has fabricated and is starting to commercialize a PIM system. As I mentioned, Samsung already started to do it, to announce their prototypes and show them at conferences. The first one was called FIMDRAM, later called HBM PIM. FIMDRAM is a more specialized system, is not so general purpose as the PIM architecture, is more focused on AI and machine learning, as you may know. It's based on HBM2 memory. And what they basically did is that for a stack of HBM memory with 8 different layers, they place some processing elements in 4 of the layers. These processing elements that you can see here, these are called PCU blocks. Each of them has access to 2 banks, and each of these PCUs is sort of a SIMD unit. It's a 16-bit floating point SIMD unit with 16-bit memory. So it's good for SIMD execution. And one interesting characteristic of this FIMDRAM architecture as well is that it's compliant with a modified JEDEC controller, which probably will be good for its adoption. If you want to learn more about FIMDRAM or HBM PIM, of course, you can go to the original papers, but this is a lecture that we provided in our processing in memory course. It's not the only proposal from Samsung, but it's the proposal from Samsung for HBM memories. But Samsung also presented in 2021 this AXDIMM system that is a DIMM-based solution. As you can see, it's a DDR sort of DIMM that contains some reconfigurable unit here inside this AXDIMM buffer. They prototyped it with this card with a standard DIMM interface and some FPGA in the middle that can access data from 2 DRAM ranks. And inside the FPGA, in the first paper that they published, what they did was implementing some compute unit for recommendation systems, and in particular to calculate to access embedding tables and calculate the SLS operator. This specific hardware can work in two different modes. There is a normal mode where the host CPU is allowed to access data in the ranks, and there is also the PIM mode. In that case, the CPU cannot access anymore the ranks, and the accelerators here, as you can see, there are actually two accelerators for the two ranks. The accelerators there can access data from the ranks and compute as is needed. And this is more or less the execution flow. In the very beginning, the host needs to write the embedding tables into the memory ranks. After that, it changes the mode from the normal mode to the PIM mode, and then writes instructions to the corresponding instruction buffer here, and then starts the execution of the SLS operator. So inside the NMP, inside the processing unit that you have in the FPGA, we first read one instruction, decode it, then fetch data from this PSUM buffer that keeps it's like the accumulator for the calculations that they did here, accessing the embedding tables from the memory, adding and updating the PSUM buffer. This is a link to another lecture about AXTIM in this case. The next real-world PIM architecture that was presented exactly 1 year ago and has also been presented at Hot Chips at the end of 2022 is from SK Hynix. It's called Accelerator in Memory, and it has similar purpose to the HBM PIM architecture from Samsung. And actually, if you look at this die photograph here, it resembles a lot the HBM PIM architecture. One key difference is that this one is for GDDR6 DRAM and not for HBM DRAM. But as you can see, it also places some processing units near the memory banks. Not one processing unit every 2 banks, but there is one processing unit per bank. Each of these, because in the end, the type of workloads that they are targeting is the same, each of these also has an array of multipliers and then another 3, as you can see here on the right-hand side. There are a couple of innovations in this architecture as well that I consider very interesting. The first one is that they have a specialized logic for activation functions, and these activation functions use access to memory to read from a lookup table, but they can also do interpolation in order to be more accurate. And they also include these SRAM-based supplementary buffers that are used to move, are used to keep some operands, for example, the weights of a neural network layer or input feature maps. And they can also be used to move data between different memory banks in a similar way as the row clone techniques that Professor Mutlu already introduced, and we will discuss later again. And this is a lecture about AIM. And the next one is Alibaba HB PNM. In this case, it's a 3D stack logic and DRAM die. As you can see here at the bottom of the slide, there is a DRAM die at the top, and there is a logic die at the bottom. The logic die is more specialized for the specific applications that this architecture is targeted at. Recommendation systems, and as you can see, it contains some specialized AIM. Go to talk the coffee and in talk about this architecture. For watching recommended there's define ranking their neural engine, if called correctly, is sort of a small systolic array. But we also delivered a lecture on HBM PIM. And there are more real PIM systems. I'm aware of at least one more from a startup in Israel that is called Neuroblade. These guys followed apparently a GPU approach. There are not many details, at least last time I checked their website, not many details about the architecture in their website, but they filed at least a couple of patents. And what the patent says is that it's a distributed processor that may include a memory array and a processing array. And the processing array is divided into processor subunits being associated with the corresponding dedicated memory array of a plurality of memory arrays. And they can also communicate. This is one of the pictures that you can find in their patent. And here you can identify the different memory arrays, the processor subunits, and this sort of all-to-all network that connects the different processor subunits. And if you look at the internals of the processor subunit, they may have different sorts of processing elements, such as, well, this one here, accelerators, etc. This picture is from their website. What we know from them is that their chips are called PIM extran chips or IEM-PU, and apparently, I'm not completely sure about this, but apparently all the different execution compute units are connected using PCI Express. Well, what can we say about all these systems that we have just very quickly covered? We can say that there are some similarities and some differences. Some of the differences is that, I mean, all of them can be considered processing near memory because they are placing processing elements near memory arrays, but it might be near the bank, as is the case of UPMEM, FIMDRAM, AIM, or HBM PNM, or near the chip, as is the case of AXDIM. Some of them are general purpose, such as UPMEM, while others are more specialized, FIMDRAM, AIM, or HPPNM. They use different execution paradigms, fine-grained multi-threading, SIMD, systolic arrays, and also the data types and operations they support might differ, right? So some of them are natively integer, some of them support floating point, and even for those that support floating point, as you can see, some of them are floating point 16 or BF16 or FP32. It all depends on the specific applications that they are targeted at. And same for the type of memory that they use, DDR4, LPDDR4, HBM2, or GDDR6. But there are as well some common characteristics between all these PIM systems. First of all, there is a host processor that might be a CPU or a GPU, and this host processor has access to a standard main memory and also to the PIM-enabled memory. This PIM-enabled memory contains multiple processing elements that have high bandwidth and low latency memory access to their corresponding local memory or memory array. Third, these processing elements are relatively slow. They run at a few hundred megahertz and have a small number of registers and small scratch pads or caches, or maybe they don't have these caches at all. And the Ps usually cannot communicate directly between each other, or at least not outside of the same chip. They usually need to communicate via the host processor. This is a picture of such kind of system where we can see the host CPU, we can see the standard main memory, and then we can see the PIM-enabled memory in different forms. This might be a DIM, or a HBM stack, but yeah, basically composed by a memory array. It can be a bank, it can be a rank, and also some PIM processing elements. And for your reference, the same list of common characteristics is copied here as well. Okay, now we are going to quickly go into the, let me know if you have any questions, by the way, about the first part. If not, we can also talk during the coffee break. Yes.
We compare performance across all these different systems, like compare one of the new PIM system versus CPU. What is the commonality across the comparison? Because one thing you can have a lot more DIMMs and higher performance, and on the other end you have a lot more CPUs and more sockets and more performance. So in this kind of future evaluation, this kind of research, how do you say, hey, this is apple to apple performance comparison?
Well, we have only worked directly with the APMEN PIN system, and that's the system that we can talk about in terms of evaluation, comparison, etc. Whether it's apples to apples, I think we can consider it apples to apples relatively. That's true. First of all, because it's not the same. The PIM system by itself, I mean, the PIM architecture by itself cannot work. It needs a CPU, but you can compare to that host CPU by alone, right, by itself. I think in that sense, it's like you compare a host processor just by itself or a host processor enhanced with some PIM-enabled DIMMs, and that's what we did in our work. That's with respect to the comparison to CPU. With respect to the comparison to GPU, I also don't think that it's 100% apples to apples. Why is that? Because I mean, on the one hand, you can consider both as accelerators that are somehow connected to a host processor, both the GPU and the PIM system. But at the same time, it's true that GPUs have much more. I mean, they have had much more development effort over many years in terms of hardware, software, and they are also using these days more expensive memories that provide very large bandwidth already. So HBM memories have already been used for the last 6-7 years in GPUs, and in that sense, I don't think it's a fair comparison. But still, I think it's good to compare them and see performance numbers from the different devices in order to have an idea of what's the potential of the PIM system. That's, I think, the main goal of comparing. Okay, thank you for the question. Okay, yes.
Thank you for introducing the PNM system based on DRAM. We can see so much industrial level dynamics on PIM bus, but they are all based on DRAM. How about SRAM? So because in ISCC every year there's quite a few papers on SRAM-based PIM chips, no matter analog-based computing memory or digital-based computing memory. But in your opinion, what is the factor that hinders that the giant, the industrial companies to develop those compact SRAM-based PIMs?
Yes, yeah, that's actually a very good question. No, we are not covering these sort of SRAM-based systems in this tutorial, even though we keep them in mind and also read papers from ISSCC. I think these accelerators are also very interesting ones. I think we can also consider them processing in memory. In fact, I think we can consider them processing using memory because you are computing directly with the SRAM cells. But in some sense, one limitation that I see in these sort of devices is that they are still pretty small. And because they are small, they cannot keep data for a very long time. They cannot keep, like many weights from many layers for a long time. So still, you need to have a larger memory that keeps the images and keeps the weights, and from time to time you move them from this memory to the SRAM-based accelerator. So in some sense, even though I think I agree with you, they can also be considered processing in memory. I see them more like an execution unit or an accelerator that could be tightly connected to a processor, but it still needs to go to a larger memory, a DRAM memory, to bring data frequently and so on. But that doesn't mean, I mean, I'm saying that, but at the same time, I think they are very promising as execution units that can be very fast and energy efficient. Yeah, but yeah, thank you very much for mentioning them, because I think they are also very, very interesting, and maybe we will incorporate them to our lectures as well in the near future. Okay. So if there are no other questions, let me start with how to program a general purpose processing in memory system. We are going to specifically talk about the APMEM processing in memory system, but I believe that many of the, a lot of the experience that we can gain and we keep gaining on programming the APMEM PIN system can be applicable to other processing in memory systems as well. The APMEM PIN system follows what we call the accelerator model, where APMEM DIMMs coexist with conventional DIMMs, and the APMEM DIMMs can be seen as a loosely coupled accelerator. What this means is that we need to explicitly move data between the main memory and the PIM-enabled memory, and we also need to explicitly launch the kernel, the function that is going to run on the PIM system, on the PIM cores. We have to do this kernel launch explicitly. In some sense, this resembles GPU computing, right? Where you need to first move the data from the CPU memory to GPU memory, then you compute on the GPU, and finally you return the results to the memory of the CPU. So, and that's in some sense as well expressed by or shown in the patent from APMEM. First of all, the system on a chip, or the central processor, the CPU, needs to load data to be processed on the DRAM memory banks, on the APMEM MRAM banks. Remember that was the name. Then the CPU transmits a processing command that launches the kernel, which is basically launching the kernel that is going to run on the DPUs, and then the computation happens in these DPUs near the memory banks. At the same time, or during that time, the processor, the central processor, the CPU, keeps checking whether the computation has finished, and at that point, when the computation finishes on the memory side, then the banks become accessible again to the CPU. Remember that this is the, okay. So remember that this is the system organization with the system on a chip, and then the different chips connected to them. For the first programming example, we are going to talk about vector addition. In this presentation, and also in our papers, you will see some of these boxes with different colors that represent programming recommendations, observations, and takeaways. I just put this here for you to not get too distracted if you see that the numbers don't follow a regular order, but that's the order that they follow in our paper. So, well, the vector addition, our first programming example. In vector addition, the only thing that we are doing is the element-wise addition of the elements in two vectors, right? So if we have two input vectors, A and B, what we have to do is partitioning them in equally sized chunks and assign of each of these chunks to the different PIM cores or DPUs. And then inside each of the DPUs, we will do the same and assign different chunks to different PIM threads that are called tasklets by APMEM. So this is the work that tasklet 0 is going to do. This is tasklet 1, and this is the same for the rest of the DPUs. This is the, well, at the bottom you can find a link to the APMEM SDK documentation. This is, of course, a very important document if you want to learn about how to program this architecture, and also if you participate in the lab this afternoon, it will be a very good reference to find what's the correct syntax for the different instructions that we need to use. Some general programming recommendations for a start. Execute on the DPUs portions of parallel code that are as long as possible. This clearly makes sense, because if you want to amortize the cost of moving data from the main memory to the PIM-enabled memory, you need to compute for a while in the memory side, in the DPUs. That's something that is normal whenever you need to transfer data to an accelerator, and it happens in GPUs as well. The second general programming recommendation is to split the workload into independent blocks so that the DPUs can operate independently. If that's not the case, then the DPUs will need to access data allocated in other NRAM banks, and that will require to access the data through the host processor, which is not going to be good for performance if it happens too frequently. The third, as you could expect, use as many working DPUs as possible, as many as you can in the system in order to maximize parallelism. And the last recommendation is to launch at least 11 tasklets, or the threads that run on the PIM core. And the reason for that is related to the number of pipeline stages, as you may remember. So when we are writing a program for the DPU, the first thing that we have to do is allocating the DPUs. That means creating a set of DPUs that our program is going to use. That's the DPU allocation, reserving those DPUs for our program. And that's something that you will have to do for sure, especially because we will have many people accessing today the server at the same time. And even though the server has more than 2,000 DPUs, but we want all of us to have or a small set of DPUs that we can use. So in principle, you will allocate just a single DPU, maybe up to 64 if you want to experiment with an entire RAM using this DPU alloc. As you see, first of all, we need to declare this DPU set that we will use later in the program, and we say how many DPUs we want in the DPU set. Can we allocate different DPU sets over the course of a program? Yes, of course we can, because we can free a DPU set using DPU free. And an example of that is to give you an example, Needleman-Bunch is an algorithm where we create, we calculate elements in a dynamic programming table. We go anti-diagonal by anti-diagonal, and the number of DPUs that we need, assuming that we have a very large programming table, dynamic programming table, the number of DPUs that we need for the computation changes over time as the size of the diagonal changes, right? So one thing we can do is in every iteration, we can free the DPUs and then allocate a new set of DPUs depending on what are the specific needs for the next kernel launch. The next thing to do is to load the DPU binary, and we do that using DPU load. Observe that the DPU binary will be in some binary file in a folder in our computer, and we use that DPU binary. And with this DPU load, what we are doing is moving the program itself from the CPU processor to the instruction RAM that each of the DPUs has. Is it possible to launch different kernels onto different DPUs? Yes, that's possible. And it's something that we have to do whenever we want to exploit task-level parallelism, or we want, for example, different programs using different DPU sets, or different users accessing the same server at the same time. You will also have the chance to practice with these CPU, DPU, and DPU, CPU transfers that are copying the data from the main memory to the PIM-enabled memory, or vice versa. There are 3 different types of transfers: serial, parallel, and broadcast, depending on how many MRAM banks are we targeting. Serial transfers, yes, a single DPU; parallel, multiple DPUs at the same time; and with the broadcast transfers, we transfer a single buffer to multiple DPUs. Here you can see the specific syntax for the serial transfers. First of all, we have DPU copy to, DPU copy from. Observe that we need to use this symbolic name that represents the start of the MRAM range that we can use, the start of the MRAM memory that we can use, the offset within the MRAM where we are copying, where we are putting the data, pointers to the main memory. In this case, we are transferring 2 buffers, right? One is called buffer A, the other one is buffer B. They reside in main memory. And what we are doing is using those pointers to copy the specific region from the main memory to the PIM-enabled memory, to the MRAM, the specific MRAM, and then what's the transfer size, or the size of the buffer that we are transferring. For the parallel transfers, the syntax is different. First of all, we have to prepare the transfer and then push it, that is executing it. And we also have to say what's the direction. It's different from the serial transfers where we have DPU copy to and copy from. Here we use this direction inside the, actually when we push, when we execute, you see, in this case it's to the DPU. But again, we need to use pointers to the main memory, offsets, and transfer size, same as in the serial transfers. And for the broadcast transfers, syntax is slightly simpler. As you can see, there is a pointer to main memory, and there is a transfer size. Observe that in parallel and in serial transfers, in parallel and in broadcast transfers, we need to indicate as well what's the DPU set. That is the set of DPUs that we have previously allocated. So we can have different types of transfers in a program, and we will have to do it for sure whenever we cannot use parallel transfers. This is just an example, a select operator where we partition the input over the different DPUs, and then because in the select operator, same as in a string compaction, we are filtering out some elements, and that depends on the values of the input. The size of the transfers for the output might differ. And if the size of the transfers differs, then we cannot use parallel transfers. That's a limitation of the current SDK. We cannot have parallel transfers of buffers of different size. They need to be all the same size. So in those cases, we need to use serial transfers. And understanding these transfers well is really important because that's the way of performing deep we want to copy from to here, we'll have to first copy to the main memory and then move it from the main memory to the other MRAM bank. In our work, we have experimented with different computation patterns like merging of partial results or redistribution of intermediate results. How fast are these data transfers? We did some experiments. I'm going to I will fly over these slides, but basically, as you can imagine, these transfers are exposing the data movement bottleneck in the end, right? Because we are using the memory bus, we are using the DDR4 interface, so the maximum bandwidth that you can theoretically achieve is given by the maximum theoretical bandwidth of DDR4. But yeah, here in the slides, you can see some of the measurements, bandwidth measurements that we did for a single MRAM bank and also for multiple MRAM banks inside the same bank. You can see how for the parallel transfers, as we would expect, as we increase the number of DPUs that we are targeting in the parallel transfer, the overall bandwidth also increases. It's a sublinear increase. That's a small issue, but still it's fine. Broadcast transfers are usually much faster because we are using a single buffer, so it has better temporal locality in the CPU cache hierarchy. And that's why you can see that it almost reaches the maximum bandwidth of DDR4. So it's not that bad. One reason for the parallel transfers and the serial, for the parallel transfers especially not being so fast is, first of all, they don't enjoy so much temporal locality in the CPU cache hierarchy, but also it's because it's necessary to transpose the data before performing the copy. As you know, usually can be one that doesn't work in the if you that to be entire words. And in order to do so, it's first necessary to transpose the data. And that's something that the runtime library does. Well, this is a link to a micro benchmark that we use to measure the CPU, DPU, and DPU, CPU transfers. Now let me very quickly go on to how to launch a DPU kernel. It's pretty simple. Remember that we first allocated the DPUs. We then loaded the binary onto the instruction RAM in each of the DPUs, and now we have to launch the kernel to basically start the execution. And to do so, we do this DPU launch. We are launching the kernel that was previously loaded onto this DPU set that you can see here that you allocated as well. It's possible to do this kernel launch synchronously or asynchronously, depending on whether you want the CPU to just stop and wait until the DPUs finish, or you want the CPU, or you want the CPU to continue running and then what's wrong here? Okay, or you want this the CPU running and then am I sharing the screen right now?
No. We should take a break soon anyway.
Yeah, we should take a break, but okay. Yeah, but I'm actually very close to the part that I wanted to cover. So if you give me just 5 more minutes, I'll be done. So yeah, well, this asynchronous execution can enable concurrent execution, task level parallelism as well, but that's not so important right now. This slide that you can check in more detail later is how to load input parameters, how to send the input arguments, those arguments to the function to the DPUs. As you can observe, we can do it same as we do for input arrays, input buffers, using DPU copy to or using these DPU prepare and DPU push. So both serial and parallel transfers. The key difference is that here we are moving the data directly onto the WRAM, the scratchpad memory in each DPU. There is where we are going to place the input arguments. Yeah, recall we were talking about vector addition. This is the kernel of the vector addition. First of all, the tasklet ID, which is a thread identifier. Basically, we are using here a single program, multiple data programming model. So we write code for an individual thread, for an individual tasklet. This thread can access data from NRAM. We calculate the exact address. We are not explicitly using pointers here, but we are calculating the addresses. This is the base address of one of the input arrays, the base address of the other array, and we calculate those addresses starting from the NRAM heap pointer, which is where the NRAM area that is available to the threads starts. And this is how we allocate memory, how we allocate the space in WRAM using this memmalloc, and this outer loop is basically distributing iterations of, in this case, the vector addition over the multiple tasklets or several tasklets that are running. Each of the tasklets first need to read from NRAM, which is basically reading a chunk of the buffer from the NRAM and putting it into WRAM. Then we perform a vector addition. We are going to see the exact code in the next slide. And after we are done with each chunk of the data, we write to the NRAM, right? From the cache in the WRAM to the whatever address in NRAM that we calculated earlier. And this is the vector addition code. As you see, is very simple code, just a vector addition that is executed by each of the individual tasklets. In order for me just to finish, also tell you that there are synchronization primitives. These synchronization primitives can be used to synchronize different tasklets running on the same DPU. We have mutexes, handshakes, barriers, and semaphores. You will have, in the lab, we are going to cover mutexes, handshakes, and barriers, and we can use them, for example, for a parallel reduction. In a parallel reduction, what we normally do is that we partition the input array across the multiple threads, in this case, tasklets. Each of them computes its local sum, and in the end, we will have to do the final reduction step. The final reduction can be done by a single thread after we synchronize using this barrier, and then we just need the one single tasklet, in this case, tasklet 0, that performs the final reduction. And we could also implement a tree-based reduction, right? Because we are using a parallel processor. So we could do something like this using, for example, a barrier-based implementation where after each iteration we synchronize, and then half of the threads or the tasklets retire, and half of them continue the execution and perform the rest of the reduction. As I said, we can implement these also using handshakes. We could do mutexes, and this is indeed one of the parts of the lab if you manage to reach to it. And about parallel reduction, which is a important primitive, of course, not only for this ABMEM architecture, but for any parallel architecture as GPUs as well. You can check this lecture if you are interested in. Okay, so I'm going to stop here. I have a bunch more of slides in this presentation, but I will upload them to the website in order that you can check them for more details about the architecture or the micro benchmark based analysis that we did, and also all the workload characterization. That's not the main goal of this tutorial. It's more oriented on learning about the real architectures and also about how to program them. But here in this presentation, you can find many links to many other resources. So thank you so much for your attention. I'm sorry that I stole half of your coffee break, but yeah, I hope you found it interesting. If you have any questions, please ask now or during the break or right after the break.
One question: what kind of debugging capability does it provide? Is it a breakpoint? Print state?
I think, well, you can, there is a debugger. I haven't used it myself because I don't like debuggers much. But yeah, you can use a debugger. I think it allows you to do step-by-step execution. And then you also do printf inside the kernel, and that's yeah, it's pretty much the same as in CPU or a GPU. So yeah. In overall, I think it's pretty easy. As soon as you get a little bit of experience, it's pretty easy to program this architecture. I would say it's easier than programming a GPU with CUDA, because here we don't need to worry about warps and avoiding warp divergence, for example, where each of the threads works independently, and you may have some issues with synchronization at some point with handshakes, for example, but other than that, I think it's pretty easy.
Just one last question.
I think I should probably interrupt because I don't want people to miss coffee. I don't know how thick they are. So if you want to get coffee, please.
Yeah, of course. Please.
Some conferences are a bit strict in how they handle coffee and food. I don't know how it has been, but you can ask it offline or next time.
Sure, we can go together. Thank you very much.